All right, so now we're on to chapter 6. Now, you'll notice that there is no chapter 5 that we're going over, and that is on purpose. Basically, chapter 5 talks about a few different distributions that we're not going to be as interested in this class. If you want to read chapter 5 on your own, go ahead, but we're going to get into chapter 6. And chapter 6 is all about the normal distribution. Now, we saw this earlier, um, the normal distribution earlier, way back in chapter 2 when we dealt with the empirical rule. But basically, this is what's going to happen. If you remember what happened in chapter 4, we listed out a bunch of discrete distributions. So we listed out all of the possibilities along with the probability that they happen. Now, if we translate those possibilities from discrete variables to continuous variables, well, we can make our ranges as small as we want. So imagine taking the heights of everybody in Michigan. Now we know the variable height is a continuous variable. So we could have heights which our categories could be like anything between 5'6" and 5'7", and then anything from 5'7" to 5'8", and so on and so forth. However, once we do that, we can get more and more refined. Instead of jumping by an inch, maybe our categories could jump by a half an inch. Or maybe our categories could jump by a tenth of an inch. Or if we had enough people, we could jump by 1/100th of an inch or 1,000th of an inch. And as we break that down, basically our histogram is going to look like something that does this to something that gets finer and finer and finer. So think about creating a histogram of the probabilities. So let me say a relative histogram. And then we know this is the bell shape. We've seen that before. So what if we break our categories up not by jumping by size 1, but by jumping by size 5, or excuse me, 0.5. You can imagine that that jump of 0.5 is going to create more bars, and they're going to be thicker, and they're going to be a little bit looking smoother. And that's what happens with our histogram. Our histogram turns in from something that looks like a bunch of bars in a bell shape to something that gets smoother and smoother and smoother. And again, as you get more and more bars, you would think that this distribution sort of becomes a little bit smoother looking. And you get the bell-shaped curve. And that bell-shaped curve is giving us the normal distribution. And so what we're going to do is we're going to pretend that instead of having a discrete variables, or instead of breaking up things into classes, let's just use continuous data, and we're going to assume that it's going to transform into a histogram with this shape if I can break it up, if I let the limit of those classes go to 0. In other words, go from an inch to a tenth of an inch to 100th of an inch to 1,000th of an inch. And we get this smooth curve. So this smooth curve is the normal distribution. And we saw in chapter 2 that the normal distribution is going to, right in the middle of our curve, we're going to find the mean and median and mode. It's going to be there. And we know something a little bit about the empirical rule. We dealt with that in chapter 2. If you recall, it said 68% of the data was within 1 standard deviation of the average. 95% of the data was within 2 standard deviations of the average, and 99.7% of the data was within 3 standard deviations of the average. All right. Now, what's that empirical rule implying? That's basically implying something about the connection between the area underneath the curve and the percentage of data that lives there. So here's where we get into the properties of the normal distribution. All right, most of these we've seen before, but I just want to state them aloud before we move on. So the normal distribution is the bell-shaped curve. We know that the mean and median and mode are all in the center of that curve, and they're all the same number. We know that the normal distribution is symmetric. Now, here's one that works differently than Chapter 4. There's no gaps in the data. So in Chapter 4, when we did an experiment like flipping a coin, we couldn't get 1.2 heads. We had to get 0, 1, 2, or 3 heads. Well, with continuous data, you can say, well, is there any heights that are 5 foot 6.1 inches? Since it's a continuous curve, we're going to be able to find a height of that size. Now, once we've seen the empirical rule, basically we see, oh yeah, since the area, let me flip back one slide. Since the area under the curve is giving me my probability or my percentage of data there, this area under the curve is essentially giving me a probability. It's giving me the probability that if you pick somebody at random from this data set, you fall within 1 standard deviation. Or the probability that you pick somebody from this data set and they fall within 2 standard deviations of the average, and so on and so forth. So since the area under the curve is giving me a probability, well, that means the total area under the curve has to add up to 1 because the total probability has to be 100%. And this never crossing the x-axis, basically that just means all of my probabilities have to be positive. So the normal curve will always be above the x-axis. The area underneath will always add to 1. And then obviously we stated earlier that it does satisfy the empirical rule that we saw in Chapter 2. Now the good thing about normal distributions is there's really only 2 types of questions that one could ask, or that I would ask about a normal distribution. The first question is, can we find the area under the curve? Another way to state that question would be saying, can we find the probability that a randomly selected individual falls between 2 different values? So finding the area under the curve is equivalent to finding probabilities. The second type of question is, can I find some sort of values on the x-axis? And these are kind of reverse questions of each other. One of them, this top one, I'm going to be giving you x values, and then you're going to find area underneath the curve. The second one, I'll be giving you an area under the curve and asking you to find the actual x values. So I say x values because when you go back and we look at a normal curve, these values will be either x values or z values, right? We saw in this case these would be z values, but if I had a different mean on this number line, we would talk about x values. So can we find the area underneath the curve, and can you find the values on the x-axis? And interestingly enough, we are going to have two calculator functions that fit each question. So anytime you're trying to find a probability, anytime you're finding an area under a curve, we're going to use the calculator function normal CDF. Now you can see the inputs there. They're low, high, mean, standard deviation. We'll talk about how to do that on the calculator once we get to that spot. The other question is going to be answered using the calculator function inverse normal. All right, again, these are kind of inverse questions of each other. So finding the values on the x-axis, we use inverse normal, and then the inputs are an area and a mean and a standard deviation. All right. Again, I'll explain that more when it comes up. So let's start with what's called the standard normal curve. Now, the standard normal curve is the normal curve with average of 0 and standard deviation of 1. Okay, this is sort of like the baseline normal curve. And why it's so useful is that any other normal curve can be transformed into the standard normal curve if we're willing to use z-values. Okay, so if you had a different mean and a different standard deviation, you could use a z-values and it would fit the standard normal curve. So standard normal curve has average of 0, standard deviation of 1. Okay. So let's take the z-scores or z-values and say, well, let's find the area. Let's find the probability that we pick an individual at random and they have a z-value between 1 and -1. Now this should look familiar because this is exactly what the empirical rule was stating. It was stating, well, what's the probability that we're within 1 standard deviation of the mean? Since we're using z-scores or z-values, a z-value of -1 means 1 standard deviation to the left of the mean. 1 standard deviation to the right of the mean is a positive 1 as a z-value. So the empirical rule would tell us that about 68% of the data is within 1 standard deviation of the mean. Now that's nice, but what we're going to do is we're going to get a little more specific. We're going to go and round our probabilities to 4 decimal places. So the empirical rule, 68%, that's like a 2 decimal place probability, 0.68. We're going to round and be a little bit more specific. We'll go out to 4. So let me explain how we do that. All right, so remember what we said, that normal CDF is the function that we're going to use. So let's find that on our calculator real quick. Remember, we're finding the probability that you pick somebody out at random and they have a z-score or a z-value between -1 and 1. So let me show you where that's located on your calculator. So what you would do is you take your calculator and you go back into the distribution menu. So we hit second distribution. You should be fairly familiar with that because we've done it with the binomial distribution and also with the geometric distribution. And what we're going to use, don't be tricked here, we're going to use normal CDF. This is a continuous function. So think continuous CDF. Now, there's 2 types of operating systems. The first type you'll see is going to have a lower, an upper, a mean, and a standard deviation. So what we would do in this case, our lower number is 1. Our upper number, is -1. Our upper number is +1. Since we're on the standard normal curve, our mean is 0 and our standard deviation is 1. Now, if you don't have this operating system, what you're going to have to do is you're going to have to type in 4 numbers. And those 4 numbers are always going to be the lower bound, comma, the upper bound, comma, the mean, comma, the standard deviation. So normal CDF does that. And you can see that the answer that we get is 0.682689 and so on and so forth. And so what that's meaning, so normal CDF, we went lower bound, upper bound, mean, standard deviation. Again, my mean and standard deviation are 0 and 1 because we're on the standard normal curve. And on the standard normal curve, they're always 0 and 1. And sure enough, we got right about 68%, 0.6827. So it's just slightly over 68%, which does mesh well with the empirical rule. Now, the next problem says, what if we included the -1 and the +1? It turns out that whether we include the -1 or we don't, our typing in is going to be exactly the same. -1, 1, 0, 1. In other words, my lower bound is still -1, and my upper bound is still +1. My mean is still 0. We're talking about z-scores again. And my standard deviation is 1. So again, we're talking about standard normal curve. So my mean is 0, my standard deviation is 1. And you might think that's a little weird. In previous chapters, whether we included getting one tail or excuse me, let me say it this way. When you flip a coin, there's a big difference between getting less than 2 heads or getting less than or equal to 2 heads. The less than doesn't include the 2. The less than or equal to does. Well, here, if we have less than 1 versus less than or equal to 1, I'm saying that there's no change. The reason for this is that property of the normal curve that said there's no gaps in the data. So if there's no gaps in the data, well, think about where 1 is. Well, let me actually go to that one. Think about where 1 is. It's consisting of just this green line, right? Since there's no gaps in the data, we can get a z-value of like 0.9999. So we can get really extremely close to 1. And because we can get really extremely close to 1, and we can get really extremely close to 1 from the other direction, we can get something like 1.000001. That little green line there, where the z-value is 1, actually doesn't contribute to any of the area. Okay? Geometrically, what we would say is that a line doesn't have any area. So since we can get really, really close to 1 from both the left and the right, and the only thing we're missing is a vertical line, and vertical lines don't have any area, we can kind of ignore the distinction between less than versus less than or equal to when we're on the normal curve. So that's kind of a nice thing. So both of these are 0.6827. Now, what I'd like you to do is I'd like you to try these next 2 bullet points. The probability that you pick something out at random and they have a z-score between negative 1.5 and 1.5. And then the probability that you pick somebody out at random and they have a z-score between negative 3.2 and positive 3.2. So go ahead and type those in, and in 5 seconds, I will start back up. All right, so basically, in this third bullet point, from negative 1.5 to 1.5, hopefully you did do the pausing. I'm going to write it down right here. So what we would do is we would take a normal CDF function. My lower bound is negative 1.5. My upper bound is 1.5. My mean is still 0 because I'm still on the standard normal curve. And my standard deviation is still 1. So we type this into our calculator. Again, it's in that distribution menu, normal CDF, and then lower, upper, 0, 1. And you get a 0.8664. Again, this is rounded to 4 decimal places. Similarly, if we were to do what's the probability that we get something between negative 3.2 and a positive 3.2, we get 0.9986. So again, maybe I should retype what I'm typing in. We would do normal CDF. Our lower bound would be negative 3.2. Our upper bound would be 3.2, and then 0, 1. Hopefully you know what I'm saying by lower and upper bound. By lower bound, what I'm saying is we have this region that we're trying to find the area of. So let's go back to the visual here. We have some region here, and we're trying to find the area of between two values, between two, for instance, vertical lines here. So we would have a vertical line and another vertical line, and what we're saying is the lower bound is the lower vertical line, the upper bound is the higher vertical line. By the way, notice what we just did. The empirical rule worked for 3 different values. It worked, said something about within 1 standard deviation, within 2 standard deviations, and within 3.23 standard deviations. And what we did by using normal CDF, now we can get something that's not just more precise than the empirical rule, but that deals with any number of standard deviations we want. So we just dealt with essentially a question which said, what's the probability that you pick an individual at random and that individual is within 1.5 standard deviations of the mean? And then this last problem could have been restated as what's the probability that a randomly selected individual is within 3.2 standard deviations of the mean. So this normal CDF deal expands our understanding of the empirical rule. Now, turns out that we don't always have to be symmetric. We don't always have to say, hey, what's the probability of between negative 1.5 and positive 1.5? We don't always have to have the same lower and upper bounds. Okay, the lower bound doesn't always have to be the negative of the upper bound. We could do something like this. What is the probability that you pick something at random and that random thing has a z score or a z value which is less than 1? So let's think through this. So if I want my I want to find the probability that something that randomly picked has a z value less than 1. So less than 1, I see a nice upper bound here of 1, but there's no lower bound going on. Actually, in some ways there is one. Let's think about what this would look like in terms of the area under a curve. So let's go back to our normal curve. We have a normal curve, and we want to find the probability that z is less than 1. Now again, we're on the standard normal curve, so the mean here is actually 0. And so 1 is probably somewhere right around here. So that's probably 1. I'm trying to get a little bit thicker marker there. There we go. So there's 1, okay? Now when we say less than 1, basically what we're doing is we're saying anything from that point all the way to the left. Now how far does this go to the left? Well, it goes to negative infinity. So it continues to go all the way to negative infinity, all right? Basically, this thing goes forever. Now, we're not going to have to deal with negative infinity. We just saw that if we go 3 standard deviations out, we get like 99.86% of the data. So all we're going to do is instead of writing down negative infinity for my left-hand value, what we're going to write down is negative some really big number. Okay? So in order to find this blue area, we're going to go our lower bound as negative some really big number. So here's what it's going to look like. We're trying to find the probability that z is less than 1. I'm going to increase the font just a little bit. So how I would do that is I would do normal CDF. My lower bound, again, it should be negative infinity, but what I'm just going to do is I'm going to put negative, what is that, 10 million, or negative a million. There's 10 million. So negative 10 million, and then my upper bound is 1, and then since I'm on the standard normal curve, my average is 0, my standard deviation is 1 again. So lower bound, if it's negative infinity, we just basically approximate that by a negative really big number. By the way, if you would have looked this up in the book, they would have told you to do negative E99. And that's basically 10 to the 99th, or excuse me, yeah, negative 10 to the 99th power. So that's just, again, another really big number. So all we're going to do when we have infinities, in this case we had a negative infinity because it went to the left forever. But if we had a positive infinity, what we would do is we just do a positive really big number, like 10 million. And so if you put in normal CDF, negative 10 million as the lower bound, upper bound is 1, mean is 0, standard deviation is 1, you get out 0.8413. Now, what I'd like you to do is I would like you to finish the other 3 problems on this page. What's the probability that you pick somebody out at random and they have a z-score that is less than or equal to negative 0.65, to positive 0.65? Then what's the probability that that person has a z-score above negative 0.34? And what's the probability that the z-score is between 0 and 0.65? Push pause on the video and I'll come back in about 5 seconds. All right, so hopefully you did that. I'm going to go straight to the guided notes and write these things down, or write this down. So when it says, well, what's the probability of getting less than or equal to 0.65? Again, we would have the same idea. This can go infinitely small, so we're going to use negative infinity or negative a really big number as my lower bound. My upper bound is going to be 0.65. My mean and standard deviation are still 0 and 1. Now, when I put that into my calculator, what I got is 0.7422. Again, that's rounded to 4 decimal places. Remember, all probabilities are going to be rounded to 4 decimal places. So that's the normal CDF. Now this one is similar, but this one gives me a lower bound. So it says Z has to be bigger than negative 0.34. So negative 0.34 is my lower bound, and my upper bound is positive infinity. So I'm just going to approximate that by a really big number. So I want to go from negative 0.34 all the way up to some really, really huge number. My mean is still 0, my standard deviation is still 1, and you get 0.6331 as the probability that you pick an individual at random and their z-score is above negative 0.34. By the way, if you were to draw this, let's undo what we did. What you would do is you would say, okay, negative 0.34 is a little bit to the left of the mean. I'm not drawing this very well, but that's fine. And we are going to go from negative 0.34 all the way to positive infinity. So we start lower bound is negative 0.34, upper bound is positive infinity. We can approximate that by a really big number. And that's all we wrote. Okay. Now, for the last problem is pretty straightforward. This one, lower bound is 0, upper bound is positive 0.65. So when we do the normal CDF, we go from 0 to a positive 0.65 with a mean and standard deviation of 0 and 1. And you should get 0.2422. Now here's what I want you to see. Notice that when we went from less than or equal to 0.65, we got a 0.7422. When we had from 0 to 0.65, we had a 0.2422. So notice they were 0.5 different. And that should make sense in terms of what you think of this picture here. Again, envision we have 0.65 as some vertical line right here. Okay? If I'm trying to find the probability from 0 to 0.65, I'm trying to find this probability in here. And we found that that's 0.244. However, notice this about the normal curve. It's symmetric at the mean. So if I were going to do this area in yellow, well, we know the total area under the curve is 1. And so that yellow area is 0.5 because the left half and the right half have to be equal. So the yellow area we know is 0.5. And then we said, well, if we had, again, 0.65 somewhere in here, I didn't, whoops, let's undo that. That was a bad line, even for me. If we had the area between 0 and 0.65 in blue, if that was 0.2422, then the area from 0.65 all the way down to negative infinity would be this blue area plus 0.5 for the yellow, which gives me my 0.7422. Now, that's not super important right now on these problems where we have to use normal CDF, but it is going to be very important on the next type of problem. And that next type of problem is the inverse norm type problem. This is where we find the values on the x-axis. Now, once again, we're going to start looking at normal curves, which are just the standard normal curve. So we're going to restrict just to the standard normal curve. And we're going to say, okay, let's try to find a certain z value. And here's what we know. We know the area under the curve, under the normal curve, from negative infinity up to a certain z value is 0.2561. Can I find that z value? So 0.2561. Let's look at this normal curve. So what is it telling me? It's saying that there's some z value down here. Let me just try to, again, create this with a marker here. There's some z value where if I draw a vertical line and then look at the area from negative infinity up to that z value, that blue area is 0.2561. All right, so 0.2561. So that blue area is 0.2561. Okay, so how do we find the z value? Well, here's how we find the z value. We use our inverse norm function. It turns out the z value is always going to be given by this inverse norm function. Let's actually make it slightly bigger. So the z value is going to be given by inverse norm, an area, a mean, and a standard deviation. Okay. Now in this case, let's actually take this way. The area that I want to use is actually the area that was given in this problem, 0.2561, 0.2561. The reason that that's the area that I want to use, it turns out I always want to use the area from negative infinity up to z. So in this case, that was the area that was given to me. Notice that if we were given this yellow area, that would have been a very different type of area. So we have to be really careful on these problems, which is the area that we plug in. And the area that we plug in is always the area from negative infinity up to the z-value that I'm looking for. So in my case, 0.2561. The mean is going to be 0. The standard deviation is going to be 1 because we're on the standard normal curve. Now, as far as inverse norm goes, I'll just show you this once. Calculator, again, that same distribution menu. You'll notice the inverse norm is number 3 on that distribution menu. Now again, there's two operating systems. One, you'll have this where it'll say area, mean, standard deviation. You just type in 0.2561 for your area, your mean is 0, your standard deviation is 1. If you have the other operating system, it should look like this, where the 3 inputs you just type in manually as area, mean, standard deviation, all with commas between them. So this is the z-value that we're looking for. Now notice that that z-value, the one we were looking for, since it's a z-value, I'll round it to 0.66. Again, probabilities I round to 4, everything else I round to 2. So since this is a z-value, it's not a probability, and therefore I'll round it to 2 decimal places and get negative 0.66. So in order to have an area from negative infinity up to the z-value be 0.2561, that particular z-value needed to be negative 0.66. Now here's where it gets a little tricky. Area to the right of 0 and to the left of the z-value is 0.3456. 0.3456. Now, this is not the same area that we talked about in the first problem. To the right of 0 and to the left of the z-value. What would that look like? Well, we know that 0 is our average. So we're going to go to the right of 0. So I'm going to be shading this way. And to the left of some z-value. So I'm going to be looking for this z-value here. Hopefully you get that, how I'm doing that. So we know that this area here is 0.3456. But that's not the area we need to plug into the inverse norm function. What we need to plug in is we need to plug in the area from the z-value all the way down to negative infinity. And this case, we stopped at 0. So basically, if I shade this in yellow, what I need to do is I need to come up with a total of the area in blue and the area in yellow. And if you think about this, the area in blue being 0.3456, and we know the area in yellow. We just discussed that. The area in yellow has to be 0.5 because that's half of the curve. So the total area in blue and yellow is going to be a sum of 0.3456 plus 0.5, which is 0.8456. So I'm going to just write that as a note. So the area we need is 0.5 plus 0.3456, which is 0.8456. Now, what I would suggest is that you try not to memorize a bunch of weird steps of when we add 0.5 and when we don't. What I would suggest is that in every single one of these problems, draw a little picture like I've been doing, and just sort of mark up which is the area that I have and which is the area that I need. I have the blue area. I need the combined total of blue plus yellow. So that's what I would suggest doing rather than trying to memorize a bunch of, well, this word means I add 0.5, this word means I subtract 0.5, and so on and so forth. So we're going to type in 0.84, whoops, excuse me, I have 2 decimal points there, I don't want that. 0.8456 into my inverse norm function. Again, that's in the distribution menu. And you'll see that this time, the z-score that I was looking for is 1.02. Again, rounding it to 2 decimal places to make it easy on ourselves. And just to reinstate what I was saying, I would have drawn a little picture in here, but it's hard to see on the computer. So that's what I would have done if I were taking notes. Draw a little picture and then write z equals inverse norm 0.8456, which is 1.02. I'm not drawing that picture because, well, I'm using I'm using that as my picture. All right, so let's look at this next one. It says the area to the left of 0 and to the right of some certain z value is 0.0233. What I'd like you to do is try to draw that area and then decide what the z value we need is. So push pause or pause on the video and try that. All right, so hopefully you did that. Let's actually 0.0233. I apologize. Let's do some undos here. So we have some z value. Now, here's the deal. The area to the left of the average and to the right of some z value. So we have some z value there. So this area here is that 0.0233 number. Okay? That is not the area from negative infinity up to z. What is the area from negative infinity up to z? Well, I have shaded it in green here. Hopefully that makes sense. But it's this area right here. Negative infinity up to z. Now, what you'll see is that in this case, there's a relationship between the green and the blue, but it's not add 0.5. The relationship between the green and the blue is that they take up half of the curve. So together, they take up half of the curve. So if the blue is 0.0233, we're going to take 0.5 minus 0.0233, and the green area would be 0.4767. Hopefully that makes sense. Again, write it down if you're a little bit confused. Continue to label your normal curve in that way. So basically, the area we use in this case, since the green and the blue added up to 0.5, we would take 0.5 minus 0.0233 and find out that the green area is 0.4767. So when I go and I plug things into my calculator, I'm going to plug in inverse norm, 0.4767. We're still in the standard normal curve, so we're still going to be using 0 as my mean and 1 as my standard deviation. When I get that out, the z-score on that is negative 0.06. So notice that that was very, very close to the average. The average, again, on a standard normal curve is 0. So that's how we find those z-values. Now, I'd like you to try this last one on your own. Find find the z-value. Again, we're on a standard normal curve, such that the area from this z-value to positive infinity is 0.7132. So push pause on the video, and I'll wait 5 seconds to pick back up. All right, so hopefully we did, or you did that. Let's go back to our drawing. Again, these are really crude drawings, but that's all we need. Okay, we don't need some really, really fancy, really accurate drawing. We just need to sort of get a conceptual idea of what's happening. So there's a z-value somewhere. Actually, I've been drawing this. Let me do this in blue. Keep drawing this in. I want to draw this in too many different colors. So we have a z-value somewhere. And the area from this z-value all the way up to positive infinity is 0.7132. So this blue area is So this blue area is 0.7132. That's not a very good 2, but that's okay. Remember, that's not what I want to plug in. Which area do I want to plug in? Well, I want to plug in the area from negative infinity up to z. Again, I'll shade that. I'll shade that in green. Now, what's the relationship between the blue area and the green area? Hopefully we can see that the blue area plus the green area takes into account all of the curve. All of the area underneath the curve, I should say. So what's that mean about the probabilities? That should mean that the probabilities add to 1. So if the probabilities add to 1, all I have to do is do 1 minus 0.7132, and I would find that that green should have probability of 0.2868. 8, this is a bad draw again, 6, 8. Trying to do it too quickly there. So 2868 is the green area. And so what I would do, again, if this were me, on the notes, I would make a note, or first off, I would draw the picture that I was trying to draw on my slide. But I would also say the area we need is 1 minus 0.7132, which is 0.2868. And so when I go for the inverse norm, I'm going to type in 0.2868, comma 0, comma 1, and that gives me a negative 0.56 as the z value for which the area from that z value to positive infinity is 0.7132. So again, if I were taking notes, I'd have a little picture trying to replicate the picture I have here. When I'm teaching in a classroom, I generally draw these things on the board. So that's what's happening. So I'd have that picture drawn on your guided notes, and then I would write down area we need is 1 minus, and then z is equal to inverse norm 0.286801. Again, I had a double decimal point for some reason. So hopefully that makes sense. What I'm going to do before we move on, I'm going to stop this video here, and then we'll move on to the next section of the 6.1 material. So I'm going to stop right here. Here now we've seen the two main parts. Finding the area underneath the curve, which is again finding probability. We use normal CDF to do that. And then finding values on the x-axis. Again, here we're using z values, but they were values on the x-axis, and we used inverse norm to do that, both in that distribution menu. So we'll pick back up with the normal distribution in the next video.